Alright, so now we're going to talk about double-ended queues, known as Deques or Deques. And what it is basically, it's like a queue, which whatever goes in first gets used first, and then the last thing is the thing that goes last. Sort of like a queue when you're standing in line at the grocery store. Sorry about the autofocus, that was actually really terrible. Um, So a double-ended queue works similar to a queue, except for you can insert to the front or the back, and then receive from either the front or the back. And I personally feel this is a valuable structure to learn just to think in complexity terms and in terms of making some problems a little bit better. However, for practical application, it's not nearly as useful as other structures we've talked about so far. One example of how it is used is in a job scheduling algorithm for scheduling for multiple processors. But that algorithm's fairly complicated to get into. It basically uses a deck of threads to be executed for each different processor, and then as it forks, it goes back into the deck, and then the deck will work with the new forks instead. And once you get to operating systems in a more advanced sense, you'll understand what that means a little bit better. So there are two common ways that decks are actually implemented. Um, One is a linked list. And, just as we talked about how we have stacks or we have queues that we use underlying structures such as a vector or a linked list to handle them and then just wrap the functionality of those, we can do the same with a linked list. Decks have options such as push front, pop front, push back, and pop back, which work on the front and the back respectively. They don't have random access. If you think about it, it works almost identically to a linked list, which makes the linked list a natural choice for implementing this, because that is basically what it is. It is a limited linked list. Um, there are other ways you do it, and for a more efficient one, because, as you know, linked list, we have pointers in memory that go to other pointers in memory to go to different nodes, and that's how you form the list. And these could end up in different pages of memory, which when you get to operating systems or machine organization, you'll understand that a little bit better. But if something's in a different page of memory, it takes more to access because you don't have the hardware cache to help you out with speed of accessing things. So theoretical time, the linked list will always win, but in terms of actual access time, you may not get as good of as strong of a benchmark as you would with the second method, which is using dynamic arrays or vectors. And you may be thinking, well, we've used vectors, and if we just wrap a vector, we actually lose a lot when we're doing these operations, the push front and the pop and the pop front. And you're right. But the nice thing about a double-ended queue is that, you're doing the same operations on the front and the back. So one very basic example of how this works is you end up with two vectors instead of one. You have vector 1, vector 2, something like that. As you're adding on, one of them is considered the front, and one of them is considered the back. And you use you use a very basic algorithm to decide which spot it ends up in. But you do push front, you push it onto here. You pop front, you pop it off of here. You push back, you put it here. You pop back. And then you have to implement logic so that when, say, back is empty and you're doing a pushback, you do have to do a resize and pop that one out instead. Let me do that a little darker so you can see it. And then ends up reading just sort of like in this direction. So your front starts here, your back goes here. Things on the end will always end up here. Things on the front will always end up here. And you can just go sort of in a circle like that to read it all if you were to decide to read it all. You also end up with, a side note, you end up with the peak and um, operations, sort of like we have on the stack, where you can peek the front or the back. Just so you can see what the front and back look like. I actually believe it's called just front and back, but as you know, I think using the word peak makes it a little more clear what that means. Um, this is the very basic implementation of it, just some arbitrarily sized front and back vectors. And you get fairly okay locality of reference, which just refers to how the memory is organized, how it is all near itself, so it's much easier to access. It's significantly faster because you're more likely to not have cache misses. And another method that uses these dynamic arrays also will do it using a dynamic array of fixed size dynamic arrays. So, a vector of vectors, if you will. So you end up having some vector, and I'm drawing it vertically here for a reason. And you have, basically, if you had two items, you would end up with what this is. And that vector would be right here. And once these fill up, you end up going into, you create more vectors, you end up in more vectors, and you end up with a better locality of reference on those vectors. So when you end up with larger loads, such as the algorithm I briefly mentioned for parallel job scheduling, you'll see this more because you'll end up with a higher amount of stuff in the cache that is near where you're looking at in the deck, which, is pretty useful because you have much faster accesses. And when we do it this way, and we access it in sort of this manner, which is sort of how that ends up, you end up not really losing anything with the front, with popping front or popping back, because your front and back are the same, or they're accessed the same. It's sort of like you have a vector that's in reverse for your front, and it's honestly quite a smart way to do it, just because you don't have to worry about the cost of resizing until one of these two vectors is empty, or one of these many vectors is empty. And the added benefit is here, when one of these is empty, you just delete it. You only have to shift one vector of a much smaller vector, and you save even more time. And that is a very basic overview of Deques. Hopefully this has been useful to you. It's not one of the more popular structures to use in general because its uses are very limited, and anything you would use this for, you typically end up using a linked list for anyways. And because it typically doesn't have a random access operator such as the braces or the .at function, you're not getting anything more than you would with a linked list, other than the specific limitations that you get from using a deck. So it's sort of like when we use a linked list as a queue. We are setting up a class to use a linked list in a specific way with a specific structure. And that's basically what a deck would be doing. But the operations are so similar with a linked list, and the way it works is so similar that if you strip out the iterators, you end up with a deck. Now, a more efficient one, obviously, is this way, but that's the point where you would actually be using a deck as a deck instead of a linked list.